Hello viewers, thanks for joining me for today's video. So this will be my final video on slab design and slab load decomposition as a subtopic to the inner workings of Prota Structure. In my previous video, I showed you the slab design and I stressed that it is very important that you always do slab type automatically so that you can have a very close design whereby if you relate it when you are doing it manually, for any software that you employ to do your structural design and analysis, the aim is to automate the process. So I want to stress again that everything boils down to the basics, how you idealize and what you expect your result to be. So today I'll be doing slab design and slab load decomposition. I want to show you some irregularities that I observed while probing the software. Now, for many of us who have gone online on YouTube or using references or attended training at one point or the other, you would have seen that there are two methods of slab load decomposition in Prota Structure. We have the yield line and we also have the finite element. So we'll go into the software and we'll see some of the things that I observed when it comes to slab design and slab load decomposition. Now, I will be talking on the slab types. We have regular panels and irregular panels. Now, when you have regular panels, it is easy when you do slab type automatically, then the software determines the operating cases for each of the slab types that you have in your model. This is a model that I have made and I have inserted slabs at different points. Now I have an irregular slab shape here, which is slab 5. And normally, as I've mentioned earlier, that when you model your slab, you always do slab type automatically. So let us observe when we do a slab type automatically for this model. Apply to all the slab in the story. I say apply. Now you can see that the software is telling me that slab 5 edge count is greater than 4 and it's saying that unspecified slabs. Now for the other slab, the software has allocated the types for each of the slabs, but for that particular slab 5 is saying that the edge count is greater than 4, so unspecified slab. Now this is a cause of concern. In this case, if you input your slab strip, which I have in X direction and in Y direction, X direction signifies the long span and Y direction signifies the short span, and that is what I have modeled here. You notice that the slab have recess in this place, so I have made this dotted line, and my assumption is that the slab comes and join up like this. So, and if you look at it from our model, this place is not continuous and this place is not continuous, so which means two adjacent edges discontinuous, and that will give us case 4. Okay, now going into the software, as I have done my slab type automatically and he has allocated and he said specify slab is equal. Now if I run the design for the slab, let's see what the short span and the log span coefficient will give us. Let's say design. Now quickly, we are talking of slab 5 in this case. Okay, now the result is coming out fine because I have done slab type 5 and I have allocated for actually for this slab. Okay, so let's say, let me close this so that I can actually show you what I mean. Let's say I delete all these slabs, I delete these slabs, I delete this slab, I delete this slab, I delete this, I delete. Now there's no slab. Let me delete these slab strips. Okay, so let's say I want to input fresh slab now. I say my slab is 150, my cover is 25, then I have 2.2 as dead load, then impose load. If I assume residential is 5, then I insert this slab in all these panels. Now okay, so quickly let's do a slab type automatically. Okay, I do slab type. Now it's saying slab 3. Now that our slab is now labeled slab 3. Okay, so slab type automatically again, unspecified edge count, S3 edge count greater than 4. Okay, fine. Now if you click on this slab and say let's see property, you are seeing that is allocating 1 after doing slab type automatically. But in the real case, this slab is not case 1. Now if you do not check this and you have assumed that since you have done slab type automatically, then you are, excuse me, you have, you are right there on the way. Peradventure, even while you are doing your slab type automatically, you didn't even check that is saying that that slab 3 is unspecified slab because the edge count is greater than 4. So you say okay, then you now input your slab strip in X direction 1 edge, and it's like this, and we now put Y bob like this, and I close. And immediately if I run my slab design and analysis I design, now if you notice that slab 3 now is now showing me that in the longer direction these are the moments and these are the moment coefficient, and in the short direction these are the moment coefficient, and this is the moment both span and support. Now again, as I have done in previous video, I have modeled out the slab in the slab analysis design QBasic software, and I have assumed that this slab is like this, ignoring this recess. I've assumed that this slab is like this, so it's giving me case 4. So I have case 4 here, 150. Again, I'm using 20 concrete and 380 strength for steel. So, and these are the coefficients: short span coefficient 0.7 and long span coefficient 0.05. Now let's see what the software is bringing. This will be for short span. It's saying 0.04 and 0.036 short span. You can see it varies. So what is using for short span is what is for long span. in this case. Now you can see that the moment for short span, for span is 12.8 and for continuous years is 7.4. Let's see what the software is saying for short span. Short span will now be X. Is saying 11 and 8, which is short of the moment I am supposed to have. And look at what he's saying for the long span, 7.5 and 5.6, which is also short of what I'm supposed to have, 11, 8, and 11. So you can see this variation in the moment, and the moment is what is used to calculate for steel. So again, if you don't check what the software is doing, you are most likely be doing something lesser or more depending on the situation you find yourself. So it is very important you check your output with what you have idealized, what is your assumption for your structure. So how do I rectify this? Now when you do slab type automatically, just as you have seen that the software is not seeing this slab, so it's saying it's unspecified. So what you do in this case is you come to that particular slab, then you now come to property and you now assign the case that you want for that particular slab yourself, which I did earlier, and that is what the software was reading. So and you update it. Now when you update, you have now specified the kind of slab that this slab is. Now when you go back and run your design, let's say only select sufficient steel. Now let's see what is now bringing. Now you can now see now that the short span X is like this, which is the long span is now 10.5 and 8, 0.04 and 0.03. So I have the long span, you can see 0.04 and 0.03, and you can see the moment span is 8 and continuous edge is 11, which is what I have here. Continuous edge, yes, and this is span 8. So let's look at the short span as well. You can see the short span now I have 0.07 and 0.05, which is what is here, 0.07 and 0.05, and you have 12.8 and 17.4 in the span and continuous edge. So which is what you have here, 12.8 and 7.2. You can see clearly by doing this, then you are sure that okay, what the software is giving you is reliable. Again, your confidence level when using the software will be on a level that you can say, okay, I have done something right. I can be sure that the output of the software is as exactly as I have modeled or I have predicted my structure to behave using all the structural engineering principle and the accompanying codes specification for any project that you undertake. So it is very important that you always check your assumption with what the software is giving you. If you have done this over time, then you working with the software will be an easy thing, as you now have a pattern of working through the software, and you can be sure that the automation which the software affords you can actually be relied on, crossing the T's and dotting the I's of what I'm showing you that the software does. Now let's move on. Like I've said, we have two types of load decomposition by the slab. We have yield line and finite element. So what it means that the load on the slab, when decomposed onto the surrounding beams, you either use yield line or finite element. Now, again, using this as a basis, so this one is saying that this is 17 that will be decomposed on the short span, and this is 21 that will be decomposed on the long span. So let's check. I will show you one thing that I observe here, which is very, very important for you. Now, edit member load. This is long span. So if I have 12 and 3 here, that's 12, 13, 14, that's about 15 for the slab load that is decomposed on that. So that is the long span. Yes, okay, so let's see. And long span is saying 21. Okay, let's see on this side. This is actually not long. Let's see what we have. We'll probably have 12 because it's having, okay, we having same. And let's look at the short span. Short span, edit member load, 11, 12, 13, that's about 14. Okay, so this one will have contributed by 3. Slab 3, let's see. Slab 3, what is slab 3 contributing? 12, 13, that's about 15. Okay, so at least I can live with that. UDL 17, 21 on the long span. Okay, moving on. Now what I want to show you is that you see in the software, I have discovered that when you use when you have yield line on this irregular beams, and you have these beams and these beams, now yield line gives you a load 22, that when you compare the yield line load with the finite element load, you have a very wide margin of the difference, and that is what I want to show you now. Now when in the different videos that you've seen, they will tell you that you use finite element method to decompose these loads. Now again, the different school of thought will tell you that the finite element that you use has lesser moment when you use finite element to do your analysis. And as much as this is the case, again, my argument always is that, okay, if I have model and I have predicted that, okay, my structure will behave in a certain way, and I'm expecting this moment, now I am getting a lesser moment. Now what is the approach? Is it being conservative or what? That's the question I ask myself. Now that causes me to probe this software with a different method. Now, okay, so let's do a quick analysis. Okay, before we do the analysis, this is loads are decomposed on this beam by yield line method, and this is the value that slab is contributing, 22 and 5. Okay, on this beam. Now let's do load decomposition by finite element and see, and we'll see some abnormalities in the load decomposition. My system is not usually like this, I don't know. So okay, let's do replace. I have done the analysis before, so but let's redo it so that I can show you what I mean. Now, like I've mentioned earlier, from different videos that you've seen, they will tell you, okay, do finite element decomposition, and we jump into the software and say, okay, finite element decomposition, they are saying 800 here, uniformity factor 250 here. I don't know, some people run this like this. I actually did it like this. Okay, so let's do, and this is my mesh, and I click OK, and it performs and it says slab loader transfer to beams. I say close, apply to beams in the model. Now let's see some abnormalities. If I click on this beam and I say edit member load, now you can see that the software, the finite element load decomposition is telling me 5213 for live load and 52 for click load. That is outrageous. And I'm like, no, this cannot be. Okay, so let's close this. Let's check this beam as well. Now, well, this thing I'm showing you always happens in a case when you have irregular shapes of slab. So you have to be very careful when you are working when you have. Now this one is showing me 15 and 3 in this case. This one is even better. So in essence, what I'm saying is that when you run finite element, even in the software, they will tell you the finer the mesh, the better the accuracy of your result. So my advice is that when you are using finite element, it is better you have a finer mesh so that you can have something close to what you have idealized and you have predicted that this is the likely result that you are supposed to have. What I'm trying to say in essence is that it is not a case whether the software gives me lesser moments when I'm using finite element method or not. It should always be a case of what you have idealized and how you have predicted that the structure will behave. So when you do, before software came, there are methods that are being used to solve all these common problems that we now use software for. So in essence, if I'm using the software, I want to be confident that the software is doing something as close, as much as it can be closer to when I'm not doing the software at all. So what I've discovered is that, like I said, the finer the mesh, which is what finite element is all about, the better the accuracy of your result. So I have tested this and I have seen that the best that can give you something close to what you want is that when you have a uniformity factor of 100 and you now have a plate size element of 75, so that gives you a final mesh. Now, like I've said, I have done this with several different different values so that I can get something as close as to what I have predicted. Now you can see finite element as well to going to use decomposition method option beam shortcut. Okay, let me say close, apply to all beams in the model. Now with that final mesh, let's see what this now gives us. You can now see that the load has now been reduced, and so what it means is that from here, this particular beam that is adjoining into this irregular shape, with the load coming from this slab, with load coming from this slab, and with the load coming from this slab, with my yield line and with the specified value of that finite element, I discovered that my results were close. There was actually little difference. So same thing, if you check this slab, you can see now that it has now decomposed the load properly on the beam. So if you check, you see yield line, you see you have 20 something here and 5 something here. So if you add it, it will almost sum up to what you have here. This is yield line and this is finite element. If I click OK, same thing. If I check this beam, edit member load, this is what finite element is giving me. Yield line, by the time I had this, it will almost give me what I have here. So I click OK. So what it means in essence is that by the time I run my analysis with this, I think I've done all the setting. Let's do a quick build analysis. I now have a moment that is as close as to if I'm having a yield line and a finite element analysis. So I don't know much, but I want to believe that for as many projects that you undertake, your judgment should always be based on what you are expecting, based on what you have idealized for that particular project. So I want to believe that it should not be a case of whether finite element gives me lesser moment or not. It should always be a case of which result is closer to what I have idealized. Now you can see using the finite element, my moment here on this particular beam is 122 and this is 22 on this beam. So let's close this and have this back, and let's now say that's for finite element. Let's now say slab load yield line. Let's use yield line for all the model. I say yes. So yield line is now operating. I now run the analysis again and let's see what the moment is saying. Let's see. Okay, hold on for a second and let the software do its thing. Okay, usually it's not always okay. So the result is out and it will display the analytical model. I close this. Now let's see again. Let's see what the moment using the yield line. Now again, now you can see that the difference is not that much in this case. This is 123. In the finite element model I have 122 and this is 27. In the finite element I think I have 22 or 25 or so thereabout. So you can actually see that understanding what the software does and how you can tweak the software to actually model your structure to behave in the particular way you have predicted it to behave. Yeah, it should be your focus. So I do not subscribe to the fact that finite element gives me lesser moment. So what it means is that in some cases, because in some of the models that I have done before, I see that even some finite element gives you more moment in some cases, while in other cases it gives me lesser moment compared to the yield line or normal analytical method. So this is another thing that I've discovered in the software. So, and this is how you can actually get around it by having a smoother mesh for your finite element. And this discovery was as a result of me, trying to, as much as possible, relate what I model or what I idealize, and if I am actually calculating these things manually. So I think with this and me understanding what I've just showed you, it gives me confidence if I'm to use this particular software and engage it for a real project. I will be sure that okay, what I'm doing is in line. So all these things I'm showing you, the ones I've showed you and what I'll be showing you in the next video and the subsequent one after that, there are things that can actually affect the output of your design. So it's very, very important that you take note of these things, and I hope this video helps you to revise how you work and how best you can utilize the software to get a better output. Remember, always remember that the software is to automate the process. So don't leave the software in its entirety to do the job of the actual engineering for you. You do the engineering yourself and let the software do the automation. Thank you for watching today's video. See you in the next video.